Okay, welcome to the second video from Chapter 9. In this one, we'll be looking at the definition of momentum and how Newton's second law relates to it. Now, you should probably remember from last year the definition of momentum, P equals mv. P is momentum. And remember that it is a vector quantity and that it has the same direction as a particle's velocity. The units are the kilogram meter per second, which is the same thing as the Newton second. Now let's look for a second at Newton's second law. What that says is F equals ma. But a is the time derivative of velocity, and that means that we can write that as the rate of change of the momentum is the force. That's really F net. So the idea is that if you have a system of particles, or a single particle really, forces applied over a time change the momentum of the system. And in order to find the total momentum of the system of particles, you add the individual momenta. So P total equals mi times vi. Now you may recognize that sum mi times vi from the last slide of video 9.1 because we said that the velocity of the center of mass was equal to that sum divided by the sum of the masses. So what we can say is that P total equals the velocity of the center of mass times the total mass. And that is quite convenient. Now in this example, which is taken from your textbook, move, you have a softball, you're given the initial and final velocities, and you're looking for the magnitude of the change in the ball's momentum. So we're looking for delta P, which is going to be equal to m delta V, or m times Vf minus Vi. Keeping in mind that Vf and Vi are both vectors, and therefore we can't just subtract 20 from 15. Instead, we have to look at the directions of the velocities. So Vi points like that, 35 degrees below the horizontal. And that means that if you work out the trigonometry, that Vi is 12.3 I hat minus 8.6 J hat meters per second. Vf is a little bit easier. It's just negative 20 meters per second I hat. That's because Vi points that way. Vf is back toward the pitcher, so sort of opposite the direction of Vi. And that means that delta V, Vf minus Vi, is equal to negative 32.3 I hat plus 8.6 J hat. If we find the magnitude of it, that's 33.4 meters per second using the Pythagorean theorem. And the magnitude of the change in momentum is m delta V, which is about 10 kilogram meters per second. Now the question is, what caused that change in momentum? And the answer to that is the force exerted on the ball by the bat. So when you apply a force to something, it changes its momentum. We can also say that that force was relatively large because the ball was not in contact with the bat for very long, presumably. And so for a force to act for a short time and cause a significant change in momentum means it has to be a very large force. Now we're going to look at the idea of conservation of momentum. And so the first thing we need to do for this is to notice that we're talking about a system of particles. So we're going to have multiple objects in the system, and they're going to be exerting forces on each other, and also there are going to be things outside exerting forces on them. So internal forces are forces that one part of the system exerts on another part. And external forces are forces exerted by outside objects, so by particles outside of the system. This makes it very important to identify what the system is. So let's say that we have a particle or a system of n particles. You have m1, m2, m3, and so on. Now they may all exert forces on each other. And so if we look at the net force on the system, that's going to be the net force on particle 1 plus the net force on particle 2 plus the net force on particle 3, and so on. But if we look at all the forces on particle 1, that's going to be the external force, or forces on particle 1, plus the forces on particle 1 from particle 2 and from particle 3. But we're also going to look at the net force on particle 2, and that's going to be an external force from particle 2, or on particle 2, plus the forces on particle 2 from particle 1 and from particle 3, and so on for the net force on particle 3. And what we'll find is that when we add these up, F12 and F21, by Newton's third law, are equal and opposite. And that means that all of the internal forces will cancel out of the sum. And the result is that the net force on the system of particles is the sum of the external forces. And so we can say that F net external on the system of particles equals the time rate of change of the momentum of the entire system. So we ignore internal forces. That's very useful. We've been doing it all semester so far. We just didn't know we were doing it. And the sum of those external forces is equal to the rate of change of the system's total momentum. The most useful result of this is that if there are no external forces, or the net external force is 0, then the total momentum of a system will be conserved, meaning it will not change. And that is going to lead us to a number of very, very useful things. First off, collisions. We'll find that momentum will be conserved in collisions, and we'll explain why in the next video. Also in explosions, which you have a couple of problems to work with, because in both collisions and explosions, the internal forces are quite large, but the external forces are not important. Also, frictionless sliding, where the momentum in one direction will be conserved. And that's important because, remember, we said that F net equals dp dt. Now if, say, the net force in the x direction, there shouldn't be a, is equal to 0, then dpx dt equals 0, and the x component of the system's momentum will be conserved. And that's what happens in these two problems, 27 and 29. Now the y and z components of the momentum may not be conserved, but if f net x equals 0, then the x component of the momentum will be 0 as well. For tomorrow, you should work questions 3 and 8.